Okay, so if we have the function, I'm going to start with the second problem. It's off the board now. You can't really see it. I'm not sure why I even did this in the video, but sketching the graph of this map, sketching the graph of this quadratic function, and then using the graph for making some estimates. So we're going to start off with this. Let's just say that the function came out x squared plus 6x minus 9. Okay, how do you graph a quadratic function? As we've illustrated, this is how you do it. Exactly what open math tells you to do. Exactly what the text tells you to do. Okay? The open math text. And if you don't know to do this, then you need to think about one. Okay? Because most of you, at least many of you, haven't, you're not really seeing this picture. Okay. You get the zeros and the axis of symmetry from the quadratic formula. I'm not going to go through the details of how you plug into the quadratic formula. People are fine with that if you know the quadratic formula. If you don't, again, think about how you're approaching the course because everybody's going to know this one. Okay. Now this is going to be 36, and this is going to be 36. That's going to give us 72. It's this, and of course, a negative 6 over 2 gives us negative 3. The square root of 72 is 6 times the square root of 2, which is going to be like 8.5. That's an approximation, but you have no real choice. You should also know that that's 6 times the square root of 2. So it's basically not sure that it's 8.5 divided by 2. And that gives you like, well, it's negative 3 plus or minus 4.8. Be like 1.8 or negative 7.8. Well, if we're asked to graph this, we draw the graph. The zeros are like negative 7.8 and 1.8. So if I put negative 8 here and put 8 out here, then this to do a little subdividing. I see what 1 and 2. I see where 4 is. 2. And we'll see if we can beat those. Negative 7.8 is close to negative 8. And 1.8 is up here pretty close to 2. So they're my zero. axis of symmetry is that -3, that's what the x equals -3 line. And of course, that comes right out of the quadratic formula. It's here. It's here. And I've described that length, why it is. Okay? Because the axis of symmetry is halfway between the zeros. And the axis of symmetry divides the thing in half so that you have mirror images on the two sides. So in any case, the axis of symmetry is at -3. So there's -3. Here's x equals -3. The zeros are at approximately 1.80, -7.80. And then your y-intercept is at y equals 2 of 0. In other words, you plug in 0 for x because that's what we have in the y-axis. The y-axis is all the points where x equals 0. If x equals 0, we get 3 of 0 equals -9. So at this point, actually, before we calculate the 0, we can sketch a parabola that satisfies the conditions we have so far. Of course, my vertex is kind of missed. Let's punch a little bit here. That's vertex. And here is point 0 and -9. That's our y-intercept. These are the zeros. I'm not going to write that on the picture, although actually, if you're doing this, that's not a good place to write them. Okay. So we have this. In the vertex, it actually equals -3. So y equals g of -3. So we plug -3 in here. It's going to give us 9, -18, and -9. Makes me wonder if I got my intercept right. Yeah, okay. So when I drew this thing, I was a little premature. If this is 0, -9, it tells me that my that my vertex is at 0, -18. Or at 3, -3, -18. And according to the way I just drew this parabola, looks like the vertex isn't that much not much lower than y equals -9, right? That might be y equals -10 or -11, but it sure isn't y equals -18. So I kind of got to go back to the drawing board. -18 would be all the way down here. Y equals -18 and x equals -3 to give me a point here. So now I have to redraw my parabola. Okay, this is a good parabola. The zeros and axis of symmetry. Do that. But the vertex doesn't quite work. Because the vertex is -3, -18, which is much lower than it was when I drew this. So I'm going to have to draw a steeper parabola. Okay, so here is my graph of y equals U of x. This white parabola wasn't steep enough. Okay. Now, if you think about everything I did here, you see how all this stuff fits together, and this is how you graph the quadratic function. Now, I also asked that you use your graph to estimate g of 5. Okay, we asked to estimate f of 2 and g of 5. And then the solutions of g of x equals f. Okay, well, this would be let's just say g of x equals 14. That's my f number. And of course, g of 5 is easy enough to consider. Okay. And you know what I really should have said was, and it's a little careless, I'm going to change this to g of -5. Because g of 5 is going to occur when x equals 5, which is about here. And the graph doesn't do it. I intended to be fairly close to the vertex. And in most cases, your vertex will be somewhere around -5. Okay. So, that correction, estimate u of x equals 14. So 14 is about this big. Of course, plus 14 would be up here. So let's just say 14 is here. That's a little low compared to the scale I have. Here's a line where y equals 14. And of course, y equals g of x. So if I want to see what the solutions of g of x equals 14 are, make sure this graph extends far enough. It looks like g of x equals 14 when x is about, well, there's 4, that's about 3. So I can say that g of x equals 14. X is about -3 because this point and this point on the x-axis give me the solution. G of x equals 14 here when x is about -9, okay? So I'm going to x equals about -9. And we could check that out. And we get x equals, and that's not -3, that's obviously +3. Solutions are approximately +3 and -9. Let's check to see how we did. I don't expect to be very close. Let's just see how it looks. There's positive 3. People want to write -3 because that's our axis of symmetry. I've got that in my head. But G of 3 is going to be 9 and 18, which is 27, right? And 27 minus 9 is 18. So G of 3 is a little more than 14, but that's not a bad estimate, considering this is a hand-drawn graph. Let's see how G of -9 works. It's going to work as well. It's going to equal 18. I'm not going to write it down until I do it. That's it's going to equal 18. You're going to get 81, right? Minus 54 minus 9, which is 81. Minus 63, which is 18. Okay. So the actual points for G of x equals 3 are probably like, instead of where G of x equals 14, are probably like -2.7 minus 17.3, something like that. Okay. 17.7. This, if you do this, shows me you understand what graphs are telling you. Shows me you understand what a graph of a quadratic function is telling you, and also how to work with the algebra and the numbers. And this is what we're trying to achieve here. So, well, the polynomial using my numbers. Actually, not my numbers, just numbers I'm trying to make up. You know, the numbers go get really big, but that doesn't stop us from sketching a representative graph and making estimates. There's the zeros. X is 7, this is 0, makes the whole thing 0. If X is -12, that makes this 0, so the whole thing's 0. And 4. So I can start getting my graph right away. So I have -12, 7 and 4. So I'm going to put -16 here. Then I'm going to put +16 about here, so that 8 will go about here. -10 will go through here. -12 will be here. -12 will be here. 4 is going to be here. 12 is going to be here. I don't have to get much more specific about these numbers because I can pretty much, just with this much of a scale, I don't have to number every number. Okay. X equals 7 is here. Let me follow code this. I'm going to circle this in yellow. And I'm going to make Illinois. Now, the position 7. You know, I might want to go ahead and subdivide the interval between 4 and 8. That would give me 6 here, and then it would give me 5 here and 7 here. So now I see where my 7 ought to be. I don't have to label these 5, 6, 7, 8. I know this is 4 and this is 8. I've got 3 marks in between. I know that's 7. And of course, I wouldn't label that, but I'm going to wait till I got picture of my graph to see where to put the label so the graph doesn't go through my label. Unlike what I usually do, I label it and then the graph always goes through. Okay, well, there we have it. -12. Well, -12 just happens to be one of the numbers that I marked here, so it's 4. I didn't plan it that way, but that's the way it worked out. So they're my zeros. Now I would label them. I would indicate that they're zeros. Solving the problem, you want to write out what you mean and what it is you're doing. This is so you will understand what it is you did and what you're doing when you come in and have a quiz or go in and take a test. If you don't write it out coherently, it's mostly maybe because you're not really understanding it, or maybe because you're understanding it at the moment, but it doesn't help you retain it, as well as writing out kind of details that I wrote on the quadratic function, okay? Write it out. Make sure you address meanings. Well, anyhow, okay, the y-intercept. So y equals f of 0. Well, f of 0 is going to be 2 times -7 to the 4th times 12 to the 6th times -4. Well, that's going to be a lot of fun for me to estimate, isn't it? Okay, but I'll try. 7 squared is 49. 50 squared is 2,500, so that's pretty close to 2,500. And that makes 5,000, okay? So that much is about 5,000. And multiply that by -4, you get -20,000. So I'm going to say that's approximately -20,000. 12 to the 6. Well, 12 squared is 144, which is close to 150. Okay, so then 12 cubed is going to be, like 44 squared. It's going to be like 12 times 150. That's about 1,800. 1,800 squared, everybody knows, is 3,024,000. 3,240,000. Okay? So I think that's about 3,240,000. We'll just say about 3 million. And that's going to give me -6 and what? 4 and 4 and it's 10 zeros. And that's going to give me -60. I want you to understand numbers. It's about -60 billion. So now we have the y-intercept right down here. I don't want to put it that low because now if I check my far left and far right behavior, I see that at far left it's going to be positive, at far right it's going to be negative. It's going to come down from here and it's got to go through these and then go on down. Okay, well, it comes down from here really fast. It's going to have to go way down below the frame here to come back up through this point and get to this one. It doesn't come down and go through this, then suddenly turn and go up here. It goes down where it naturally wants to go. And if you're not expecting to be really good at figuring out where that would be. But one thing I don't want you to do is try to make every graph have its low point or high point on the y-axis. We talked about that. So I'm going to put this point maybe here. So this is -60 billion. I'll write it like that. Your calculator is going to give you -6 times 10 to the 10th. Okay. That'd be okay too, if you understand scientific notation. And that's neat if you do. Okay, now I want to draw my graph. Okay, well, my far left behavior goes like this. My far right behavior goes like this. No. Really ought to stop and think before I write things down. Okay, my far right behavior goes like this. Okay, so I can say, and you know what? I'm wrong. That isn't my far left and far right behavior, but it has to be. So let's see what in the world is going on. Because this thing is going to be negative at far left, it's going to be positive at far right. I get negative 60 billion. And I do get negative there. And no, I don't. Messed up my calculation here. I'm so busy doing the numbers that I put a negative in front of that 20,000. And it's positive. So this should be positive 60 billion. Now, you see the mistake I pretended to make, right? I pretended to make a mistake there, but it didn't fit. In order to go through this point and these points, far left behavior would have to be kind of like this. And it doesn't work. On the other hand, as we're going to see, I don't necessarily go through these points. Still, I was having trouble seeing how this graph would look. It would actually go through here and come back up. But it's actually going to come through here and go back down. And how it's going to get back up there. So you got to think about these things. I got to think about these things. Okay. That negative 20,000 came from the negative 4 there. So it is negative 60 billion. So I can keep it there. Okay. And that's what I did that. Well, it turns out that my far left and far right behavior are not what I said. Turns out that they're like this. And like this. Far left behavior I'm going to say this implies you got a fourth power and a sixth power and a first power of a negative number. And then that's multiplied by the 2 out there. That's a multiply. What's the fourth power of a negative number? Well, it's positive, right? And the fourth power or the sixth power of a negative number is positive, is an even number of a negative is positive. Okay. We're running out of time, so I'm not going to be able to write all this up, but I'd write the far right would be the fourth, sixth, and first power of a large positive number. That should say a large negative number. Now, that was going to be really huge. Excuse me. Yep. Well. Okay, actually, I'm wrong. Thought we were about out of time. I just took a quick glance clock while I was thinking about this. And I did this before. I actually ended class half hour. Still got a half hour. Okay. So I'll probably write it out. Okay, so got a large negative x. If x is a large negative number, every one of these factors is a large negative number, right? Or at least the x minus 7, the x plus 12, and the x minus 4 are large negative numbers. Of course, this large negative number is raised to the fourth power, which gives an unbelievably large positive number. This one to the sixth, which gives an even larger, enormously larger positive number. But x minus 4 is still negative. So we have a positive number 2 times a negative number to the fourth, which is positive, times the positive number here times a negative number here. Okay? So it's negative, so that's what we indicate here. I'm going to see that reasoning in your paper. Because again, if you don't have that reasoning, you don't necessarily understand it. Now you could say, oh, there's a rule that says if you add up all the powers and they're odd, then all those powers would add up to a negative number, okay? Better off if you understand that, because you don't understand where the rule comes from, which is not difficult to understand. Then you can easily misuse it. So I recommend you understand the rule. Although if you just quote the rule and use it right, okay. If you quote the rule and make a mistake, it's your penalty. And it would be if you just made an honest mistake. And of course, it's honest. But, now, let me just digress for a second. The test is not going to include this, okay? Midterm. It doesn't include this. I think it might include the quadratic. It includes some things about quadratic functions. Go by the document that I sent you last weekend, okay? If it's not covered in that document, then it's not going to be covered in the test. And if it is in the test, but it wasn't covered by the document, then I won't count it once you got it right. Okay? I haven't really made that comparison, but I'm 99.9% sure that since everything is pretty much equivalent to what we did in the fall, that, I think I got it right. Okay. Anyhow, the far right. You got power as a large positive number, so you get a large positive number. Now you want to write out a little more than that if you really want to convince me. So how are we going to do this? We might be tempted to come up through here, right through this point, right? Not going to work because we go through this point. How are we going to get back here? We get back here, we'd have to come around and come back down through the x-axis, right? But we don't have a zero. These are the only places where this function can be zero. If x isn't one of these numbers, then this product is not zero, right? The only way, if x is anything but 7, negative 12, or 4, then all these numbers, none of these numbers are going to be zero. When we multiply, we're not going to get zero. That's just, pure common sense. So try to think of it that way. So this means that we better be able to come up here and turn around so we can come down here and then come up here. Now, is that justified? Because we know that that can happen. Well, we got a fourth power here, right? Well, fourth power is an even power. And that means in the neighborhood of this graph, it's kind of like a parabola, which is an even power. Except it's a fourth power, so it's a little flatter than the parabola and so forth. But it means we're going to come up to this point and we get to turn around here. And we explained that last week. And if you didn't get it, well, go by the rule. Okay? So we have to turn around and then come back up through this point. So we're going to have to do something like this. And then up here. Now, when we get to this point, what are we going to do? Actually, yeah. When we get, I was thinking you have to go down over here. I'm not with it. So when x equals 4, we're going through like an x minus 4 function, right? And that's an odd power, which means that we get to go through the point. Then we got to turn around and come back down here. But at x equals 7, we got a 4th power. Okay, and I think I said that wrong over here. We said at the negative 12, that comes from this thing. It's actually a 6th power, which is also even though. So it turns around at this one, and it comes up through here, down, turns around quickly, so come back down here, then go on up. So there's your graph. Now, you're asked to estimate solutions of f of x equals this number. And actually, I need an extra set of parentheses. And this would equal this should have been D. And you write this more. That's intended to write it up around later. Should be the quantity. You don't have to know why I chose these numbers. That's a little bit complicated. But C times D times A is, in this case, just 7 times 12 times 4. And that should be raised to the B plus A power, and that's to the 10th power. You know, that number is going to be way too big. Okay, so I can give you a good rule here. So let's just say that's not a good result. Okay. I'll just make up a number. Now what's f of 2? Okay. F of 2. Well, f of 2 is the point on the graph where x equals 2. If I come down here, at this point, y equals f of 2. If this is 60 billion, what's this? A little more than a third of 60 billion, which would be 20 billion. Let's say that's approximately 25 billion. Well, we could plug 2 in here and see what we got. Okay. That's the answer. Okay. Unfortunately, 14 squared is close to 200. And 200 times 200 is 80,000. And 200 times that is 16 million. Everybody knows that 5 to the 4th is 625. 4 times that is about 2,500, say. And 2,500 times 16 million would be about 3.2 billion. Shouldn't be that big. 200 third would be 8. Oh yeah, okay. Yeah. And my estimate should have been I think about it, 20 or 30 billion. In other words, if you calculate this in your calculator and label this and then estimate this based on this scale, do we see how 25 billion might be a pretty good estimate? And if this is 60 of something, negative 60, then this ought to be negative 25 on that thing. So that should be negative 25 billion. That should be about negative 25. Now, the whole purpose of this is you should be able to estimate from the graph. You should be able to estimate f of 2. You should be able to estimate f of 10. Okay? You should be able to estimate f of any reasonable number. Now, when you get way out here, it's hard to see just how steep this thing gets. So you wouldn't expect to be able to do a really good estimate. Let's say of 12. Or or an equation. Okay. And if we had let's say f of x equals $10 billion. Well, we would, that means y equals 10 billion, right? And if y is 10 billion, well, that's about 1/6 of this. A third would be about there, 6 would be about there. I'm going to say maybe 10 billion. On this line. So it looks like that should occur at 3 values of x. It should occur at this value, and this value, which means maybe at x equals 4.3, x equals 7.6.2, and x equals 8.5. Now, if you have a quadratic function, then you want to see where its values are, whatever y value. You can solve a simple quadratic equation. If you want to see it for a function like this, you're going to have a hard time finding it, okay? Now, maybe an estimate just gives you the picture that you need to understand what the function is telling you. Gives you a reasonable estimate. But if you check out the estimate, I can plug 4.3 in here, Let's look 6.2, I can plug 8.5. I recommend you might want to do that just to see how close I got. But I don't expect to be all that close. Okay. I think I got kind of close to this. These are a little harder. Okay. Well, that's really pretty much everything you need to be able to do with polynomials. Once you have it in factored form, you should be able to graph it, taking account of the multiplicities. The book gives you rules. I've talked more about why the rules are what they are and the meaning of the rules. But the rules are not that hard to follow if you sort them out. Okay, so you might want to start with the rules and then think about why the rules work. All right. Okay, we want to talk a little bit about complex zeros. Give you a little more reasonable function. Okay. How are we going to find the zeros of this function? Well, it should be clear that if this expression is 0, you have a 0. Then that makes the whole thing 0. Or if this thing is 0, you get the whole thing 0, right? Change my wording here just a little bit. Let's just say f of x equals 0 if and only if this is 0 or this is 0. That makes sense? Because if this is 0, then you multiply by 0, and if this is 0, you multiply by 0. There's a name for that. It's a zero property of multiplication as your text and your sort of resource. Okay, so that's it. I'm not going to belabor the quadratic formula. Everybody knows how to use it, or absolutely should. You know, pretty much everybody does. Okay, so there are zeros at -3 and -2. So immediately I can start drawing my graph. But I don't want to do that until I find out what zeros I get from this function. Okay. But if -3 is here and -2, we can have a couple of zeros kind of close by. X squared plus 5x plus 9 equals 0 if and only if x equals -5 plus or minus the square root of 5 squared minus 4 times 1 times 9 over 2 times 1. That's -5 plus or minus the square root of -11. Uh-oh. What are we going to do about that? Put a negative under the square root, under the radical. Well, that's not going to help with the graph. You're not going to get points on the graph from this. But I could write the square root of negative 11 is the square root of negative 1 times the square root of 11. Square root of negative 1 we call I, imaginary number. This is something you should certainly know when I give you this course, but in case you don't. Now, this is again something you see in algebra 1 or algebra 2. Standard topic. If you've had those courses, and hopefully you have, then that should be somewhere in the recesses of your memory. If not, prominent in your memory, depends on how long ago you had it, how much was emphasized. Yeah, that shouldn't have been a negative there. This part root of 11, obviously. Right, yeah. And there's my I. You know, that's not going to appear in the graph. But the negative b over 2a does kind of tell you that this thing is going to tend to have the relative maximum or minimum near x equals 5/2. So anyhow, if I put negative 4 here, put 4 here, 2 goes here, and negative 2 goes here, and then we go 1, negative 1, 3, and all that. So these are units. So if this is negative 4, you're going to have a 0 at negative 3, another one at negative 2. Your y-intercept is going to occur when x equals 0. And have a 0 is 54. I don't want to put that on my y-axis just yet, because I want to see some indication of how the rest of the graph is going to work. But I know that I've got to go through these 2 points, either coming up and going back down, or going down, going back up. Now, also I'm going to put my 2.5 here. This is the axis of symmetry. Actually, it's 2.5. the axis of symmetry of your x squared plus 5x plus 9 function. Because right there it is. Yeah. Now, the zeros here are imaginary, so we're not going to have, if the graph is not going to go through the x-axis anywhere over here. So, for example, if the graph comes down from here, which it does, then comes back up through the y-axis, and it's going to tend to dip down a little bit before it goes up again. And because it's going to tend to have either a vertex in this direction or a vertex in this direction, somewhere close to this. So now I can do my far left and far right behavior, and we are almost out of time. So the far left and far right are easy to figure out here. Because of the x squared, both of these are positive, no matter whether x is a big positive or a big negative number. So you're going to have product of two big positive numbers on both ends. Those are going to be your y values. So the graph is going to go up on both ends. So if I want to draw the graph now, I'm going to just come down through here somehow, then back up through here, and then maybe dip a little bit here before I go up again. So I'm going to sketch a graph that looks kind of like this. And just show it goes back up. It looks something like this. Okay, now the assignment on complex zeros, I really want to wait at least a few days before you do that one. Because I'm going to make some changes because there's some stuff in there that requires you to do some factoring that I don't think you should need to know how to do. Okay? I don't think it's necessary. I don't think it's profitable. So one concession I'm going to make, things that I usually like to cover in this course, due to various factors, we're going to kind of bypass that because even if you were to take the engineering calculus course, you wouldn't really need those techniques. Okay. They might come in handy on occasion, but they're not difficult techniques. And if you're prepared enough to do an engineering calculus after completing a pre-calculus sequence, you're not going to have any trouble picking them up. And if you're doing an applied calculus, you're not going to matter at all. Okay, so we're trying to prepare you for calculus. I don't like not doing this stuff. And if you're going to be a mathematics major, you're going to pick it up in no time at all. So it's easy stuff. We're not going to talk about it. We could maybe talk about it. We're not going to actually do it. So give me a few days to get that assignment straight the way I want it. And also to move some assignments around. I think I said earlier that there's sort of an amnesty on assignments. The assignments that you find that are due prior to next Tuesday, including assignments you've already done, maybe I'm going to move the due dates on those to the Tuesday we come back from break. Because I know studying for the exam and everything else goes on right before break can be a bit of a strain. So if you need that extra pressure relief, I'm gonna delay those. I won't delay them any further. And I expect you to have assignments done by that point. So I'm going to do some rearrangement, but for assignments that have been due so far, that just involves I'm going to extend the date, and if you want to work on them some more, you get to. If you haven't started them yet, well, I understand, given the circumstances. Okay, so I'm going to give you that little break there. Okay.